In the last video, we talked about antiderivatives, and I introduced something called the power rule. So we're now going to kind of formalize this with some notation. So basically, the second half of calculus, you're talking about things called integrals. And the derivative and the integral are kind of the two main concepts in calculus. And as it turns out, they're related to one another, and they're related by the fundamental theorem of calculus. And what you find out is that integrals are related to, the integrals of a function are related to the antiderivative of that function. And we're going to see that when we get to the end of this section here, or the end of this chapter, the end of chapter 5 in the textbook we're using. So we're gonna add to this idea of antiderivatives some notation, okay? So and then so basically we're gonna let little f of x be the derivative of capital F of x, such that if you take the derivative of capital F of x, you get little f of x. So f of capital F of x is the antiderivative of f of x. So if you take the derivative of capital F of x, you get little f of x. Okay, so the indefinite integral of little f of x is given by this. Okay, so the notation here, this is like think of this as an elongated s, and you're going to find out in the next section that the integral is related to the idea of taking an infinite sum. And so so this elongated s, it looks like that because that s stands for a sum. And so what you're going to say is the integral of f of x, and so you put the function inside the integral with respect to d of x. So the d of x, it's kind of like dy dx, and that bottom is the dx there is what you're taking the derivative with respect to. So it's the derivative of some function with respect to a particular variable, and that's the same here with the integral. You're going to integrate f of x with respect to the x, with respect to d of x. Okay? So that's the idea here. So you have an elongated s over here, you have a d of x over there, and so I kind of think of it as that these two kind of fit together. Kind of a beginning, an elongated s, a d of x at the end, and inside here you put whatever function that you're going to integrate. Okay? And basically the integral here of this function is its antiderivative. Okay, it's the function that when you take its derivative, you get this. But there's an infinite number of these, but they all differ by just a constant. So the antiderivative is always the antiderivative of this function plus c. Okay, so if I took the derivative of this entire thing, I would get the derivative of f of x plus, and then the constant would just go away. And the derivative of f of x is little f. Okay, so in other words, the derivative, if you take an integral and you get the antiderivative, if you take the derivative of this, you get the original function that's in here. Okay, so with this idea, then, we could state the power rule for antiderivatives as follows. We could use the integral notation. So if I take the integral of x to the n, so some power of x, with respect to x, it's going to equal x to the n plus 1 divided by n plus 1. And then all of that plus c. So this is basically the power rule we used in the last video for finding the antiderivative of a power. Okay? And so this is just writing it with the exponential notation. Okay? So let's try a couple examples. So I want to integrate x to the fourth with respect to x, and I'm going to use the power rule, so I would get x to the 5th over 5 plus c. And that would be the answer here to this indefinite integral. So this is the indefinite integral here of x to the 4th. Okay? So now if I'm going to do the indefinite integral of the square root of x, well, the square root of x is just x to the 1/2. So I'm going to integrate elongated s, x to the 1/2, with respect to x. And now I use the power rule here. So if I add 1 to 1/2, I get 3/2. So I'm going to get x to the 3/2 over 3/2 plus c. And then I could simplify that as 2/3 x to the 3/2 plus c. So this would be, this indefinite integral would give you this antiderivative. Okay, and if I took the derivative of this, I'd bring down the 3/2. That would cancel out. Subtract 1, I'd get x to the 1/2. The plus c would go away, and I would just be left with the square root of x. So when you take the derivative of the indefinite integral, you get the function that's inside this integral notation. Okay? So now, there's basically a couple properties we want to look at, or a couple rules, and these are the, excuse me, these are actually, I mentioned these briefly in the last video, and we just kind of used them informally. So this would be kind of the formal statement of these, and it would be a way that you could write it out. Now, you don't have to write out everything I write out this time. You can skip steps, but this is the idea, okay? This is the logic behind it here. So the rules are basically kind of like with derivatives. There was a constant multiple rule. So for indefinite integrals, there's a constant multiple rule. So basically, if you integrate some constant times f of x with respect to x, then you can pull the constant out of the integral. You can pull it out front like this, and then you're just integrating the function, and then you have the constant times the antiderivative of that. Okay? The other rule is like a sum difference rule, and we also had this for derivatives. If we integrate the sum or difference of two functions, or if we have the sum or difference of two functions inside an integral, then we can split this up into two different integrals. It'd be the integral of f of x with respect to x plus or minus the integral of g of x with respect to x. So basically, you can pull out constant multiples. You can split up an integral over a sum. Now, what you cannot do is split up an integral over a product, okay, or a ratio, or if you have a quotient. Okay, like for this one, I couldn't just integrate the top and integrate the bottom. You could not do that here. And you cannot split it up over a product, just over a sum and difference. So the logic here then is if I want to integrate this second rule says you could split this up into three different integrals. So now if I have this, the first rule here says I can pull out constant multiples. So I would get, here I'd pull the 3 out, and then I just have x squared d of x. And then I'd pull the 2 out, and then I just have x d of x. And then here, you could pull the 1 out or whatever, and you just have the integral d of x if you wanted to. Or I could just, if I wanted to, I could write it like this. You can actually have the integral d of x. That's kind of weird, but this just means you have a 1 in there. I always write 1 just because it doesn't look right to me otherwise. And so basically I use the power rule here, and that multiply by 3. So I'd have 3x to the 3rd over 3, like that. And then for this one, I would have minus 2 and then this looks like I would have x squared over 2, and then this would just be plus, and with a 1 there, you would just have x. Okay, because if you take the derivative of x, you get 1. And then you would have a plus c. So you'd get this. And this would actually simplify down pretty nicely, because these get rid of. You know, when I wrote that example down, I wasn't thinking of that, but it sure did. Plus c. So this would be the antiderivative, and if I took the derivative of that, I would get what's inside the original function. Okay, so basically, I would probably just go from here to here. I would just do x cubed over 3, and I'd know that would cancel out. And then I'd have x squared over 2, and I know the 2's cancel out. That would just be x, and I'd put a plus c. So I wouldn't write these steps each time, but that gives you the logic behind, okay, I can only do it if it's a matter of pulling out constants or splitting up over sums and differences. That's only when I can do it. In other words, I can't pull out a function. I can't pull out anything with an x. Okay, and I can't split this up over a product of two numbers, or a product of two functions, or one function divided by another. You would have to do something else. Okay. Okay, well, what about this one here? Well, this one, okay, I can't split this up over the division here, but what I can do is I can simplify the inside, and that's what I'm going to do. So this is basically like x squared over x to the 1/2. This would be plus 1 over x to the 1/2. So I split this up over the numerator. This is dx. So I split the numerator up over the denominator, and I changed the square root of x to x to the 1/2. And then what I can do here is I can simplify this by subtracting exponents. So this would be x to the 3/2 plus, and this would be x to the negative 1/2. And then I'd have d of x. Okay, so now I'm going to integrate each of these pieces. And if I wanted to, I could split this up like this, x to the 3/2 dx plus square root of x to the negative 1/2 dx. And now I'm just using the power rule twice. So this one would be x, adding 1, 2 over 2 here would give me 5/2. All of that over 5/2. Plus, this would be x. If I add 1 to negative 1/2, I get 1/2 over 1/2. Okay, plus c. And you only have to do 1c. Because if you had a plus c for this one and a plus c for that one, the two plus c's would just add together to give you another constant. Okay, so you just add the 1 plus c. So then I can invert this. I can simplify this. This would be 2/5 x to the 5/2. And this would be plus 2, and you could do a square root of x if you wanted to, plus c. Something like that. Okay? And so this would be the antiderivative of that. So with the power rule, and with some of these properties, there's a lot of integrals that you can integrate. Okay? There's a lot that you can actually find the antiderivative for. But there's going to be a lot that you can't. And as it turns out, going backwards and finding the integral is a lot harder than going forwards and finding the derivative. In fact, when you find the derivative, there's a set of rules that you apply to all derivatives, and you get to all functions, and you get its derivative. I should say a set of rules for the functions that we know how to integrate. For the functions we know how to take the derivative of, there's a set of rules that we can apply and get the answer. But it's not true the other way around. You don't tackle each one the same. So what you're going to see is that it's going to be a lot harder to go backwards, because each one is like a little puzzle, and you got to figure out how to go back. but there's going to be tools to help us do that. So in the next section, we're going to be looking at something called substitution. That's going to be the first tool that you're going to learn, and in a sense, it undoes the chain rule. You can think of it as undoing the chain rule. So as far as undoing like the product rule or the quotient rule, those are going to have to wait for Calc 2. So what we're going to do is just learn this stuff here, a few antiderivatives of trig functions, exponential functions, and then this substitution method that we're going to learn in the next set of videos. And you're going to be able to do a lot with that, but again, you're not going to be able to do everything. And then here's the important thing to understand is that there are some functions that you can have inside an integral where you wouldn't have any problem taking the derivative of that function, but as far as going backwards, it does not have an antiderivative. And so let me just give you one example. This is a classic example. If you wanted to find the antiderivative of this, okay, now you wouldn't have any problem. You would use the chain rule here to take the derivative of e to the x squared. No problem. So this seems like a simple enough function, okay? But there is no antiderivative. There is no function whose derivative gives you this. So some functions don't even have an antiderivative. And that's another thing that makes integrating difficult, because you got to recognize what you can and can't integrate, and then what sort of method you can use to go backwards. And in this case, this is one of the classic examples of a simple function that doesn't have an antiderivative. So